Hello and welcome everybody to Advent of Code 2022 day 19. Things are going a bit off the rails because it's actually the 21st. I'm only now doing day 19. So I was 1 day behind, now I'm 2 days behind. I did actually finish this yesterday. I just didn't have a chance to actually record the video for it. And also I had to I had the code written and everything. I was working with my part 2 solution takes 5 hours to run, so I just left it running overnight. I had no idea if I was going to wake up to a right answer or not, or if it was even going to be finished, but it did finish overnight in 5 hours, and it did give me the right answer, so that's a relief. Yeah, so you can probably guess that I didn't come up with a very optimal solution for this. The solution I came up with does obey all the rules, and it does work. It is just a little bit slow. There are some optimizations you could do for it that would definitely would make it work, but I just didn't have the didn't have the heart to really think through more optimizations and test them, because I was banging my head. I tried a bunch of different things and none of them were really working. So the most dumb optimization I could come up with got me the right answer and made it run in an actual time where you could just sit and watch it run. So I just left it at that. I'm going to talk through it anyway, and I'll talk about where my solution falls down and where you could add in some extra optimization, where the root of really what the optimizations are is. So with that said, let's have a look at today's problem. So day 19, not enough minerals. So in the last one, we saw that there were had these lava droplets that were created, and basically there's all these minerals have been thrown out, and you want to you have these there's these geodes that have been formed by the lava, and you want to crack them open to get what's inside out. So you're going to need a geode cracking robot to do that. But unfortunately, you don't have a geode cracking robot. You need obsidian to make a geode cracking robot. So you need to make an obsidian collecting robot to make a geode cracking robot. But to make an obsidian collecting robot, you need clay. So then you need a clay collecting robot to make a obsidian collecting robot to make a geode collecting robot. And you also need ore to create a clay collecting robot. So you might see where this is going. So we're told that we have one ore collecting robot to start off with. And we have a little factory module where we can make one robot if we have enough resources to make it every minute. We also have a bunch of different blueprints, which are basically their sets of requirements for the amount of resources it takes to make each different type of robot. So this is pretty much your input. You can see here the sample input. We've got 2 different blueprints, and each one has a set of numbers that correspond to the resource costs to make different robots. So essentially our job is to figure out which of these blueprints we should actually follow. And the way we figure out which one we should follow is in 24 minutes. So we were told that each blueprint, as you go through it, 1 a minute. So each robot that you have that generates a resource generates 1 resource unit per minute. And we're also told that when you want to make a new robot, if you have enough resources, that takes 1 minute to make. So we have this limit of 24 minutes. And we're basically going to do a loop 24 times to see how many geodes we can end up generating after the 24 minutes. But of course, there's multiple branching paths in this, and that's where the problem gets tricky. So yeah, your task is to figure out for each of these blueprints what is the maximum number of geodes you could collect in 24 minutes. And they give you an example of how you could do that, one path for doing that. So you start off with 1 ore collecting robot. He collects 1 ore. You now have 1 ore. Minute 2, you have 1 ore collecting robot. Collects 1 ore. Now you have 2 ore. Minute 2. So at this point, you spend those 2 ore and you get a clay collecting robot. Your ore collecting robot collects 1 ore. You now have 1. Your new clay collecting robot is ready. You have 1 of them. Now in minute 4, both of our robots both collect 1 resource of their type, and they increment those values. So you can see this kind of just goes on and on and on. And effectively, you just have to simulate these rules for, you know, up to a maximum of 24 minutes and see what your state is at the end of it, which is the amount of resources you've collected. The problem is, and this is where our branching logic comes in, there's a case where you don't spend any resources that you have, and there's also a case where you do spend those resources and you build a robot that you can build. So the question really becomes, just because I have enough resources to build a robot doesn't mean that I should spend them now. Or the other cases are, should I just keep spending my resources over and over and over again to build any robot that I have available? But in that case, you might not ever actually reach a point where you're collecting any geodes, because you might be wasting all those resources just making more and more ore collecting robots over and over again, and you won't actually get any geodes out of it. So you have to simulate all these branching conditions, which for this, it's pretty colossal, and it takes a very long time if you were to try and simulate every possible combination of them. So with that said, you need to now come up with some optimizations so that you don't actually have to simulate every single one. So let's have a look at the code, see what I did, and see where I started to put in some optimizations and where those could actually be improved, because in my case, it's still very slow. So part one. First thing I'm doing, basically I read in my input files and I create these blueprints. So I use this thing in here where it's basically I create the blueprints based on these keys, these symbol keys in Ruby, which I represent as their, down here, ore, clay, obsidian, and geode. And each robot, I also create a set of robots, and they have the same keys because it just makes referencing between them easier if I make the symbols all the same. And the same up here in the blueprints, I do the same thing, but it's just with these are effectively the costs of each of those robots. So I've got that data structure set up. I loop through each of the blueprints that I have, starting off in our initial state. So the resources we start off with, everything is 0. The robots we start off with, we have 1 ore collecting robot. All the other robots are 0. And that's pretty much everything for the initial state. I have an empty state here, which I'll come to in a minute, but this is basically how we're going to track our progress on it, called best. You'll see in a second. And then effectively, once this loop is finished for every single blueprint, I should have the maximum number of geodes that were cracked from each of those blueprints. And then at the end, I just do this calculation that they tell you. That gives you your answer, your score at the end. So the meat of this is in this recursive function in here, which at the end of it, so once this, I call this build function, and this will simulate the 24-minute cycle over and over again for each blueprint. And when it exits, it will give you you'll be able to find the best, amount of geodes you can get. So what does it do? There's a couple of things. So fundamentally, all it needs to really do is every time you call into it, you just need to pass in the state in terms of the resources, the robots, and the time, and the blueprint that you're interested in. And then for that, the first thing you need to do is you need to determine, can you afford to build a robot? If so, what robots can you afford to build? So that's all this loop does. It uses the cost that it comes from the blueprint, and it looks at your current resources, and it just creates a list of all of the robots that you could build if you wanted to. I do the collection of the amount of the robots that I already have. So this just increments each resource type based on the number of robots that you have, which is nice and easy. Then this is where the recursion comes in. So this is where you have a choice. For every robot that you can build, will you build that robot or will you not build any robots? Those are the choices you have at any given moment. So you can build, there are 4 different types of robots. So when you're in here, the biggest value that this can have is 4. So you can possibly build one of any 4 of these robots. 4. There is then the 5th option is you don't build any robot. Effectively, you need to simulate every single one of those for every single choice. So when you have enough resources, eventually you have to simulate all of these to get yourself to cover every single possible outcome. Now you can't cheat this, but I didn't come up with a reliable way of doing it. So the way I was thinking about it of cheating it was, well, maybe if I have a certain amount of resources, I won't bother building that robot anymore, because I know that I'm not going to need any more resources, because I couldn't possibly consume the amount of resources that I already have, things like that. So there are clever ways to do it. I didn't come up with one that I could work reliably, so I've just left it as I always try every single robot that I can build with the number of resources I have, along with the case where I don't build anything. So these recursions, then that's how we get our loop, and we eventually get down to the bottom. The two optimizations that I did to try and speed this up, one here I've called geodes. This is really just a cache. So I'm pretty much just caching the state that I pass in. So I have this cache key up here, which is generated by just the resources, the robots, and the time all stuck together. And if I see that I've already hit that cache key before, I'll just return. I'm not certain how often that actually happens, because I don't know, I think the paths are probably relatively unique. I'm not certain if it's really that helpful, but I did it anyway. It's a common enough thing that I would do if I was in a very deep recursion. I would add this caching to try and speed it up. Not really sure if it helps anything in this case. The other thing, though, that I did do to try and speed it up is this best hash, which I talked about. So what this does is, for each timestamp you're at, that the time becomes the key, so it's 1 to 24 are the keys in it, I store the highest number of geodes that I have at that time. And so that every time the loop enters, I check and see, well, have I got an entry for this? And then I check the amount of geodes I have, and I'll update that value if it's better, if my current number of resources is better than the best that's already been there. If it isn't, then I return out of it, because I know that this loop isn't going to get me there. Now, this isn't quite right, because there is a case where, say, maybe you were like 10 in and you have 5 geodes. So there could be a case where I'm 10 in and I have 4 geodes, but if I actually kept these two simulations going further, the lower one would actually overshoot the higher one, and I would actually end up being better. So the optimization here for that, so the rule is that I subtract 2 from the best and then check that. So I allow myself to be, at most 2 behind the best, and then I jump ahead. So it still cuts off a lot, because if you're say 4 behind the best, then we're like, no, there's probably no chance you're going to catch up to that. This was kind of a heuristic. I sort of just tested it, trial and error, and it does cut down the search space, but it also doesn't speed it up a huge amount. But it does still deliver the right answer, because you can change this, make it quite aggressive, but then you'll start getting the wrong answers, because you'll start cutting off branches too early, start pruning branches too early that actually delivered favorable results. So yeah, that's about it. It's a bit messy. It's not great. It does work, but it's extremely slow. So I have it set up so that it'll output onto the screen. So you see there, it ripped through a bunch of them really fast. So this is blueprint 1. These are the cache keys that it's determining, and this is printing out every time it finds a better max value. So it prints out this rank. So there we go. We found a better rank, or so actually we finished there. That's up to number 2. So in number 1 for the blueprint, I found that 9 was the optimal that you can get, which is what the sample says, which is correct. And then I've entered into blueprint 2, and again you see here the best for a good while is 0. Then eventually it starts to find some better ones. So at 19 minutes it found a 1, and then at 20 minutes it found a 1. Sorry, 20 minutes it found a 2, 21 minutes finds a 3, and so on and so forth. And now we're at a 24 and it's found a 10. So now we're actually getting into heavier branches to calculate now, because the next one's down. This will finish at 12. So it's going to compute another branch, and then another branch, and then another branch. And it will get there. It's just kind of slow. So that's where we really need to up this optimization. So that works. Not great. I'm gonna kill it just because it'll just run there for another couple of minutes. So let's have a look though at what they do for part 2, because they don't actually change it that much. But if you have a more optimized solution, your solutions for both are practically identical, can be practically identical. You just need, if you had a very good, well optimized part 1, the part 2 will just be solved more or less instantly with the same code. So let's have a look for part 2. So for part 2, they switch things up. They want you to now simulate 32 minutes. So for 32 minutes, you can bet the amount of branches gets a hell of a lot bigger than it was for 24 minutes. So this is where I'm saying that if you have a well-tuned, optimized thing, it might run a little bit slower, but it should still be able to complete. Mine is not so much. So it goes from completing in, you know, maybe 10 minutes to taking 5 hours for the 32. So that just shows you how many more branches there are and how poor my pruning approach is. They also only want you to do it for 3 blueprints. So they say, forget about most of the blueprints. We just want your top 3 blueprints. Calculate the values for each of those, and then that can be it. So yeah, the exact same approach. Other than that, there's just 2 things changed slightly. So if we go back to my code, it's the exact same, except I've added in, so you'll notice in this one, I added a minutes thing and a maximum number of blueprints to calculate. 24 and 30 is for the first part. For the second part, they changed to 32 and 3. Effectively the same loop in here. It's all the exact same. And then at the very end, they tell you instead of whatever formula they gave you to calculate, you just multiply the 3 numbers together and that's your answer. And that works. But again, it takes an extremely long time for me. So if I run the part 2 with an input, it'll start. It actually gets pretty far pretty quickly. So it gets all the way down to a best for 32 of 27. This will finish at 32. This number will go to 33 for me, and that will be the best. So that we've already gotten up to 30. So it completes this part pretty quickly, but then I think it gets to, in the my second blueprint takes, oh, it takes so long. It takes hours to complete. It gets to about 8 pretty quickly, and then it sits there and just sits there before it's able to get up. It only has to get up to 10 to be the optimal solution for this, but yeah, it's it's not great. So like the other thing as well is that this could just be my optimizations and heuristics that I kind of put in here might just not work particularly well for this set of inputs, but for another set of inputs it might actually find the paths quicker, that kind of thing. So maybe it'll be faster for some other people's inputs, but for mine it is not. But yeah, that's about it for day 19. I'm not going to claim that I had any kind of real clever insights to this. I just got it done, and that's about it. So I'm going to have a look at day 20 now, and maybe I'll finish day 20 today and be able to film it today and release 2 videos today. Who knows? Or maybe not. Anyway, we're still going, we're still moving, and I will see you guys, who knows, tomorrow, the next day, maybe later on today. See you later.